What is the single greatest oversight in the history of the universe? Back in 1985, scientists believed they had finally uncovered the answer. A team from the Harvard-Smithsonian Center for Astrophysics, led by John Huchra, had just completed an extensive observation of tens of thousands of galaxies in the direction of the constellation Coma Berenices. While they were organizing the data, a bizarre phenomenon began to emerge: a colossal shape stretching across millions of light-years. It resembled a human figure, a stick man with a slender torso, outstretched arms, and leaping legs. However, this was no mythological creature, it was one of the first superclusters ever observed. More importantly, it was not an isolated case. We eventually discovered that about 10 million such superclusters exist within our observable universe. Each contains thousands or even hundreds of thousands of galaxies, including our own Milky Way, which sits on the periphery of the Laniakea supercluster. These structures are unimaginably vast, the smallest span millions of light-years of interwoven galactic threads, while the largest extend up to 10 billion light-years with a mass exceeding a quadrillion suns. We name the nearest ones after the constellations through which we observe them, such as Coma, Virgo, Boötes, Centaurus, Pavo, and Indus. More distant ones are typically designated by numbers unless they break a record, like the Ghidorah supercluster, one of the largest ever found, discovered by Japanese scientists in 2002 and named after Godzilla's three-headed rival. Despite their ability to harbor countless galaxies across vast distances, these superclusters are actually small in the grander cosmic scheme. In the universe, there exists a scale far beyond them, the voids. The truly largest structures are characterized by an absolute absence of anything. The story is long, so let us begin this journey into the cosmic dream, but before that, please remember to like and share. While these superclusters are immense, they are not the most magnificent structures in the cosmos. The true titans are the voids. These are not mythical beasts or cinematic monsters, but their polar opposite, hollows within the darkness. Most of the universe is, in fact, empty. Voids contain no starlight, no ribbons of gas, and cannot even be observed directly, we only discover them by mapping where nothing exists. Cosmic voids are the largest structures in existence. They dictate the distribution of superclusters and shape the very nature of our reality. Everything we know, including our solar system, the Milky Way, and even entire superclusters, is essentially suspended on the edge of these voids. Ultimately, the fate of the entire universe will be decided by these empty spaces. Turning back to 1978, astronomers Laird Thompson and Stephen Gregory embarked on a grueling task. At the Kitt Peak National Observatory southeast of Tucson, Arizona, they spent nearly a week observing through the night to precisely record the positions of dozens of galaxies. After confirming their locations, they fed the captured light into an early electronic intensification device, a precursor to modern digital cameras. This technology allowed them to see extremely faint, distant galaxies deeper than ever before. They were peering into the depths of the universe where humanity had never trod. By magnifying the light and passing it through a spectrometer, they could measure the redshift of galaxies and calculate their distances. At that time, there were no computers or complex algorithms, everything was done manually. Their goal was to map a slice of the universe, recording both position and distance. While previous studies existed, Thompson and Gregory utilized two novel techniques. The first was light amplification, and the second was not a technology or a theory, but a visualization method, the pizza slice diagram. With Earth at the tip, the positions of galaxies unfolded from near to far. This simple composition was revolutionary, allowing the overall scale of cosmic structure to be presented in a single, clear image for the first time. They originally intended to study the famous Coma cluster to distinguish between true cluster members and background field galaxies. Instead, they stumbled upon something else, a massive empty region devoid of any galaxies. A place that should have been filled with stars was completely vacant, a flaw in the cosmic fabric. This new mapping method made the hole strikingly obvious. In the diagram, dense black dots marked the Coma cluster, surrounded by scattered galaxies, but in the center, there was nothing. They gave this blank space a name, the void. When they published their findings, the astronomical community was skeptical. Many flatly rejected the idea, arguing that our measurements of the universe were already clear and that galaxies should fill the sky. They suspected an error in the observation design or a psychological trick of the eye. Some believed deeper observations would reveal the void as a mere misunderstanding or a sensationalist claim. At the time, the prevailing view was that the universe could not have such large empty spaces because nature abhors a vacuum. The void they found simply should not have existed. Months after Thomson and Gregory published their results, astronomers and theoretical physicists from Estonia and the Soviet Union conducted independent observations in another direction and reached similar conclusions. Although they did not use the pizza diagram, they also recorded massive gaps in galactic distribution. More importantly, unlike their Western counterparts, Soviet scientists had been actively searching for these structures. At that time, the mainstream Western cosmological theory emphasized large-scale homogeneity, believing that on a large enough scale, every region of the universe should be statistically identical. While local density fluctuations like clusters were known, the overall distribution was expected to be uniform. To many European and American scientists, voids simply did not fit their models. However, Soviet theorist Yakov Zeldovich proposed a different model for the evolution of cosmic structure. He argued that large slabs of matter would continuously fragment into smaller clumps, such as clusters and galaxies. In this model, voids were a natural consequence, an inevitable byproduct of cosmic evolution. It wasn't until 1981, when American astronomer Robert Kirshner conducted another observation in a completely different direction, that the Western scientific community began to accept the reality of voids. He and his team discovered the Boötes void, which remains one of the largest ever found. This void was larger than any galaxy or cluster, dominating the entire sky within their field of view. The void originally found by Thomson and Gregory was formally named the Coma void. These two massive holes forced astronomers to acknowledge their existence, leading to deeper questions: how did these voids form? More importantly, how could a supposedly uniform universe allow such massive irregularities? Since the discovery of these giant voids, cosmology has undergone a paradigm shift. We no longer see the universe as an ocean of randomly distributed galaxies occasionally forming clusters. Instead, the universe reveals a more exquisite architecture. Clusters still exist, but they are no longer isolated points, they are nodes connected by cosmic filaments of galaxies. These filaments interweave to form robust structures that span the cosmos like a massive web. Even larger than these structures are the gaps between them, those initially doubted and eventually accepted voids. These voids pushed cosmologists to rethink the structure of the universe. By the 80s and 90s, scientists realized that the universe might still be called uniform, but only if you zoom out to a truly gargantuan scale. Clusters are not the limit, even the smallest cosmic voids far exceed them in volume. These voids are not isolated, they form a greater whole alongside clusters, filaments, and walls. Mapping this larger structure, including both the voids and the clusters, became the new challenge. With each subsequent observation, more and larger voids were discovered, some even dwarfing the Boötes and Coma voids. With every new discovery, scientists ask the same question: have we found the limit? Is there a critical scale where the universe finally becomes uniform? In pursuing these answers, astronomers realized they were entering unknown territory. They began to understand that the universe is not as smooth and orderly as once imagined, it is more like a vast, evolving, and boundless web. We do not know who created the Lennox globe, but it dates back to around 1510, less than 20 years after Columbus reached the New World. On this globe, the outlines of Europe, Africa, and Asia are roughly accurate but significantly distorted in proportion. South America is only partially depicted, North America is a string of islands, and Australia and Antarctica are entirely absent. In the regions of the East Asian coast, known then only through the tall tales of sailors, there is a Latin inscription, "Here be dragons." Although this phrase appeared on very few maps, the attitude it represented was common in medieval cartography. It was an era of global exploration, trade, and conquest. Every voyage revealed more of the world but also uncovered more unknown blanks. Faced with these unmappable areas, cartographers had a choice of what to draw. Their answer was to fill the space with dragons, sea serpents, and lions, partly to spark curiosity about the unknown and partly as a warning that danger lay beyond the borders of civilization. This fear of the unknown did not vanish with the end of geographical exploration. The nearest large astronomical structure to our local group is a cluster called the Virgo cluster, named after the constellation it resides in. Galaxy clusters are the largest gravitationally bound structures in the universe, acting like dense galactic cities that can contain thousands of galaxies and span millions of light-years in diameter. The Virgo cluster is about 65 million light-years away. At this scale, we truly enter a cosmological perspective. The Virgo cluster itself is the core of an even larger structure, a supercluster. Superclusters are the most densely packed regions of matter in the universe. These structures are not yet fully locked by gravity, meaning the galaxies within them are still forming and have not been completely pulled together. They are still developing. Our home supercluster was named the Virgo supercluster, a name that is somewhat redundant since the Virgo cluster sits at its heart. This supercluster contains our local group and dozens of similar clusters. However, recent research has revealed that the Virgo supercluster is just a branch of a far larger structure named Laniakea, a name meaning immeasurable heaven. Laniakea has 4 major branches, including the Virgo branch. Each branch is large enough to be considered a supercluster in its own right. The entire structure includes about 500 galaxy groups and clusters, with over 100,000 galaxies forming a massive, branching, and intersecting system extending over 500 million light-years on each side. Comparing Laniakea to a single galaxy is like comparing a city to a single person. Considering that each galaxy contains hundreds of billions of stars, Laniakea is like a megacity housing trillions of lives. Its star count is comparable to the total number of ants on Earth. Beyond it lie the Hercules supercluster, the Shapley supercluster, the Perseus-Pisces supercluster, and many more. Further out, known superclusters are so numerous that we no longer name them all, identifying them only by numbers. All these interconnected superclusters form the largest structure in the universe, the cosmic web. This web is composed of superclusters connected like vines, stretching across the entire 95 billion light-year span of the observable universe. Within this web, superclusters are linked by filaments of galaxies, and between these filaments are massive galactic walls that divide the universe into distinct regions. The scale of the cosmic web is indescribable. Comparing the Milky Way to the cosmic web is like comparing a cell to the human body, and even that fails to capture the true proportion. The cosmic web is so vast that a single galaxy is just a tiny point of light. Yet, despite the awe-inspiring nature of these superclusters, their volume in the universe is almost negligible. By volume, the universe is almost entirely empty. Aside from galaxies buried deep in the cores of clusters, most galaxies actually live on the edges of voids. Thus, the name cosmic web is perfect. Like a spiderweb, the silk is visible but occupies very little space. While glowing galaxies illuminate the filaments and clumps, they are insignificant compared to the voids. Mapping the voids nearest to us is difficult because they are so vast and empty, requiring large-scale integrated observations to outline. The shape of a void is typically spherical. The nearest one to the Milky Way is called the local void, with a diameter of nearly 200 million light-years. Further out are the northern void, the southern void, the giant void, the Boötes void, and the coma void. As we peer deeper, we continue to find more of these vacuums irregularly distributed between superclusters. They are not entirely empty. Early astronomers were surprised to find this, but they certainly lack galaxies. Countless microscopic particles, hydrogen and helium atoms, cosmic rays, neutrinos, and the afterglow of the cosmic microwave background radiation all pass through these voids. However, the density is extremely low. By cosmological standards, if a region's average density is less than 20% of the cosmic average, it is defined as a void. The average density of the universe is already sparse, about 1 hydrogen atom per cubic meter. In contrast, the density of an average galaxy is millions of times higher. This means deep within a void, aside from the occasional hydrogen atom or cosmic ray, you could be millions of light-years away from any galaxy or celestial body. This is the loneliest place in the universe. These cosmic voids are not just empty spaces between galaxies, they are also almost entirely devoid of dark matter. We know that dark matter accounts for most of the mass in the universe, with over 80% of the mass in every galaxy and cluster being dark matter. It is a completely invisible substance composed of particles that modern physics has yet to identify. Dark matter does not just exist within galaxies, it forms the backbone of the cosmic web. The galaxies we see are merely small beacons on a hidden dark web. Thus, the entire cosmic web is constructed of dark matter, and voids are places where almost no dark matter exists. We cannot observe dark matter directly since it emits no light, but we can use computer simulations to reconstruct the full picture of the cosmic web. In these simulations, the densest dark matter regions correspond to galaxy clusters, and the dark matter filaments correspond to the galactic ribbons, while in the empty voids, dark matter distribution is at its lowest. Projects like the Sloan Digital Sky Survey have already identified tens of thousands of voids in the universe, yet these discoveries represent only a small fraction of the whole. The smallest voids are 20 million light-years in diameter, often buried as small gaps within superclusters. The largest voids span immense cosmic scales, separating different superclusters by distances of 1 billion light-years or more. It is within these massive voids that we encounter a difficult problem. While early cosmic simulations could explain the formation of voids and superclusters, observations show that some voids are simply too large, so large that they exceed our understanding of the laws of cosmic evolution. They perhaps should not exist. Some voids are not just large, they are impossibly vast. These are known as supervoids. Imagine a massive cave hidden beneath the earth. In Vietnam, a logger searching for timber accidentally found a cave entrance. He heard the sound of rushing water and, driven by curiosity, stepped inside. It was pitch black, but the airflow told him he had entered a massive space. The strong wind felt like it was coming from an underground abyss. He returned home but forgot the location, only finding it again 20 years later in 2008. He eventually led the British Cave Research Association into the cavern. Several expeditions revealed its full scale. Sun Duong, meaning mountain river cave, is the largest natural cave in the world, even possessing its own ecosystem and climate. It remained hidden underground for millions of years, almost unknown. The universe hides similar things, massive caverns between galaxy clusters that we call cosmic supervoids. They are larger than any galaxy cluster and are spread throughout the cosmic structure. We are only just beginning to realize their depth. However, these supervoids did not start out this large. Like clusters, filaments, and walls, voids have an origin. They began as tiny quantum fluctuations in the early universe density variations within the primordial quantum foam. 13.8 billion years ago, during the epoch of cosmic inflation, these infinitesimal perturbations were amplified. This hypothetical event, occurring less than a second after the birth of the universe, expanded the cosmos by an unfathomable factor, stretching subatomic quantum fluctuations into macroscopic density variations. From that point on, evolution was surrendered to the whims of gravity. Regions with slightly higher density exerted a stronger gravitational pull, attracting more matter and initiating a runaway effect. This process eventually gave rise to the cosmic web of galaxies, clusters, and filaments. Conversely, the regions of slightly lower density, the voids, became increasingly desolate. Much like a small underground stream gradually erodes rock to carve out a cavern, cosmic voids were systematically emptied of their contents. Matter was drawn away toward the surrounding structures, leaving the voids to grow ever larger. Unlike galaxies, which experience violent collisions and mergers, voids expand slowly and steadily. When a wall of galaxies separating two voids is eventually thinned out as its members are pulled toward higher density nodes, the two voids merge into a single, larger expanse. There are no dramatic explosions or collisions, only a relentless expansion of nothingness. This blurred boundary made it difficult for scientists to define a void until recently, when cosmologists borrowed a technique from geography, watershed analysis. In geography, researchers use watersheds to track the flow of water, helping us understand ecosystems and groundwater distribution. A watershed is a region where all precipitation flows to a single outlet, divided by ridges or high ground. For instance, rain falling on the American continent flows either to the Pacific or the Atlantic, with the Rocky Mountains serving as the Great Divide. By applying this logic to the cosmos, treating high-density regions as peaks and voids as basins, scientists can analyze the flow of matter. Imagine pouring water onto the universe. It would naturally drain from the high-density ridges into the depths of the voids. This cosmic watershed technique provides a definitive way to outline a void, defining it as the region of lowest density bounded by surrounding structures. Using this method alongside data from projects like the Sloan Digital Sky Survey and the Dark Energy Survey, astronomers have identified thousands of voids in our local universe. Intriguingly, these spaces are not entirely random. Even within the silence of the voids, faint red galaxies persist. The distribution of these galaxies within the voids is far from chaotic. Detailed analysis reveals that they form a miniature version of the cosmic web, a web within a void. There are delicate filamentary structures, and between these tiny threads lie even smaller subvoids. It is akin to a massive cave system where a central hall is connected to countless smaller chambers separated by thin walls. Simulations suggest that cosmic voids possess a multi-layered, nested structure. There are secondary voids within primary ones, and tertiary voids within those, exhibiting a fractal-like self-similarity. Although we cannot directly observe all these layers because most dark matter is invisible, the few galaxies that emit light allow us to trace the outlines of this complexity. This raises a fundamental question: does this nesting have an end? Is a giant void like the one in Boötes the ultimate limit, or is it merely a component of an even larger supervoid? Clues to this mystery may come from an unexpected source: the cosmic microwave background, or CMB. This is the faint afterglow from 380,000 years after the Big Bang, a relic from a time when the universe was a hot, dense plasma. As the universe expanded and cooled, the plasma became a neutral gas, making the universe transparent and allowing photons to travel freely. The CMB is nearly uniform but contains fluctuations at the 1% level, representing regions that are slightly cooler or warmer. One particular anomaly, known as the cold spot, is so large and cold that it defies standard cosmological explanations. While some suggest it is a bruise from a collision with another universe, a more likely explanation is that it is the signature of a massive supervoid. As CMB photons travel through such a vast emptiness, they enter a shallow gravitational well. Because the void is so large, it takes hundreds of millions of years to cross. During this time, dark energy causes the void to expand and the gravitational well to flatten. When the photons finally exit, they must climb out of a shallower well than the one they entered, resulting in a net loss of energy that we perceive as a cold spot. This structure is known as the Eridanus supervoid, but it is not alone. Others, like the Canes Venatusi supervoid, also called the giant void, span over 1 billion light-years. Perhaps the most controversial is the KBC void, proposed in 2013, which suggests we might live inside a void spanning 3 billion light-years. This could explain the Hubble tension, the discrepancy in our measurements of how fast the universe is expanding, since expansion rates might be slightly higher inside a void. While the KBC void remains debated, the existence of other supervoids already challenges our understanding of cosmic homogeneity. In cosmology, the principle of homogeneity states that on a large enough scale, the universe should look statistically identical everywhere. This scale is generally thought to be around 300 million light-years. This is based on firm theory: if you zoom out far enough, every slice of the universe should contain a similar mix of cities, villages, and open spaces. However, supervoids are now being found that far exceed this threshold. This forces us to ask, are these just statistical outliers, or is our model of cosmic evolution flawed? If a cave on Earth were discovered that was deeper than the crust itself, we would have to rewrite geology. Similarly, voids that are too large might imply the existence of a fifth force of nature or a hidden form of energy. Regardless of the debate, one thing is certain: these voids are still growing. In the cosmos, there are forces whose very nature is to expand and consume. While biological entities are limited by resources, nothing stops the endless expansion of the voids. We live in an expanding universe where every day is larger than the last. In the late 90s, astronomers discovered that this expansion is actually accelerating, a phenomenon attributed to dark energy. Dark energy is thought to be a property of space itself; even a vacuum is filled with it. It exerts a repulsive effect that is negligible in dense clusters but dominant in the vast reaches of the voids. This means the voids are the true kingdoms of dark energy. They are not merely waiting for galaxies to move away, they are actively pushing their boundaries outward, thinning the surrounding walls and snapping the galactic filaments. As the universe ages, voids will grow, and dark energy will become even more dominant. Scientists believe that about 5 billion years ago, dark energy took control of cosmic evolution, signaling the beginning of the end for structure formation. The grand superclusters will never truly merge, instead, the growing voids will isolate them, tearing the cosmic web apart until only lonely islands of galaxies remain in an infinite, dark sea. This is the ultimate fate of the universe, the triumph of the void. Yet, ironically, these voids are our best windows into the past. While galaxies are messy and complex, filled with the noise of supernovae and magnetic fields that obscure their origins, voids are pristine. They are cosmic time capsules, relatively undisturbed for billions of years. By studying these vast, quiet regions, we can isolate the effects of dark energy and test the limits of our theories. For decades, voids were ignored as mere map errors or statistical accidents. Today, with missions like the Euclid Telescope and the Nancy Grace Roman Space Telescope, voids have taken center stage. We are learning that to understand the deepest mysteries of the universe, we must be willing to face the abyss. We once wrote "Here be dragons" at the edge of our maps. Out of fear, now, we realize the true unknown is not a monster, but the silent, cold expansion of the void. That concludes our journey for today. May you have sweet dreams, and I will see you in the next episode.